We're really thrilled that so many people are here. We just expected, like, I think 5 to 10 guys, so thanks for showing up. And just to give us a general idea of the audience, lift your hands. Who's never used Houdini? Hands up. Okay? Okay. Who's just started out using Houdini? That is cool. And who's been using Houdini for a longer time, say 2 years? Okay, cool. I think we brought something for everyone. So before we get started, just to give you a general idea of what's happening here, we're going to talk a bit about who we are, what we do. We talk about our approach when learning Houdini, when diving into problems, when problem solving. And we will give you a practical example that we have in production, which is solving growth and solving infections. But before we start all this, a short disclaimer. You might have seen this diagram. This is a diagram of where planes that made it back to base in World War II had been hit by artillery shells. So where would you put armor on that plane? Well, the obvious idea would be to put it where most shells had hit, right? Wrong. The thing is, the planes that didn't make it back to base had been hit here, here, and here. So what I'm saying here is, although we are standing here, and although stuff worked for us that we're presenting here, it might not necessarily work for you. So make up your mind, just take away stuff that seems as it would work for you, and just don't let yourself be fooled that all of this might work for you. So what is this Entagma thing we're talking about here? And we have a slight identity crisis looming here, because on the one hand you could say we're just two dudes doing tutorials in our spare time. However, when we were confirmed to talk here, we went through FMX'S speaker database, and we were like, okay, let's stalk the other guys. Let's see what they put up on bios and summaries of the talks. And I mean, FMX has a huge database, huge. We noticed something when going through the other speakers' bios. There were words like kick-ass, world-class, cutting edge, phrases like pushing the boundaries, and we're like, oh okay. So it dawned on us, we need a cutting-edge, kick-ass intro that pushes the boundaries. Thank you. So what we did here is we pulled phrases from FMX's speaker database. And this is really manual work. I was just too stupid to do it automated. So I just went there manually, copied out phrases that seemed to fit, and just threw them in some arrays here, and then just wrote an artificial unintelligence. So just a random generator that puts descriptions and bios and summaries out. And here's what we came up with. For example, employing computer scientists, Entagma, Casey Neistat's arch nemesis, is now available on creative technology companies to deliver visual experiences in onboard computer systems for 2 national space programs. And I was like, that's not that bad, especially the space part. And everything except for this sentence here comes out of the FMX speaker database. It's in there. So we gave this another try, and this is what we came up with. As a visual storyteller, Entagma, Vimeo's best channel, is the content production division of the 16-camera Google jump rig working on all 6 Bond actors. And yeah, you're like, I'm not too sure if I personally want to work on all 6 Bond actors. I'm not sure they're even all alive. So we tried to run this another time. It turns out the script is fucking sexist. For over 26 years, Entagma, like Tinder, only for Houdini, is following its worldwide comedy hits, Equal Opportunity for Women. And you're like, fuck it. We should stop this and focus on the talk, actually. So here's the dilemma we're facing constantly. It's like, how do you come up with work that has an impact, work that's actually, that evokes some reaction out there? And when you take, for example, this piece, our approach is this. We try to pair visually intricate structures with simple setups, with simple lighting, simple scenes, simple camera angles. And the issue when working in your standard 3D app is it's a generalist tool. It's like your Swiss Army knife. There's a bit there for everyone. But when you're trying to come up with intricate structures like this, you get a problem. So you might find yourself hopping back and forth into tools like 3D Code or ZBrush to come up with stuff like that. Then you sculpt it, re-import it, have to make sure all your shaders still work, go back sculpting, etc., etc. It's a pain. Especially when you try to animate this. I mean, how would you animate this? In this case, I ended up just cutting out the floating bits and pieces and just move them around so they seem floating. But had I to animate this whole structure, no clue how, at least not in my standard 3D app, because it's a generalist tool and it's good at that. On the other hand, the approach would be to take that generalist tool and try to hack it, try to wrap your mind around it, try to abuse it so it spits out what you actually want from it. In this case, I had to use standard particles and the hair system actually to mesh this, because otherwise I wouldn't have been able to mesh this. So you're constantly trying to how you recombine stuff in your standard app, because it's just not. It's meant for a generalist. It's meant for it as a generalist tool, and it's not there to put out that intricate work. Or take this example. This is. I just love bubbles. You might have seen that from Entagma. This is just a setup that intersects some bubble clusters, physically plausible, physically correct, actually. And it's nothing more than just a bit of vector math and some booleans. Yet in your standard app, you end up with something that looks like this. And you're like, okay, this is just cosine, sine, and then a few booleans, and it already looks like that. So my point here is, in order to push your standard app, you have to get into the nitty-gritty details, and it gets tedious at a time, which is exemplified in what Manu tried with circle packing here.
Yeah. I was always very intrigued by circle packing. These are very old layouts I did with standard tools, just a particle system, and tried to make the stuff not interpenetrate, which is just hard. There are many algorithms out there for doing this sort of thing, but all of these are either not very good or not very fast or hard to implement. It's really a very special problem, because what I want to achieve is visual complexity. I want to have a lot of elements, and I want to put variants in my pictures, because variants, everybody knows this from 101 design, variance, contrast is what gives your pictures interest and life. How do you bring this variance into your pictures? You can do the manual approach like an artist, a classical painter, and I do this often in 3D code, where you can just place all these little balls by hand, and your brain can decide where to put the little balls, and it will look very interesting and with a lot of variance, but it's slow because you have to do it all by hand. And what if I don't want to have one donut packed with spheres, but 100 differently packed with spheres? Then I end up just placing little dots forever and ever. So, of course, you can hack your standard 3D application that is not made for stuff like this, and you can come up with something like this. This is a dart throwing algorithm that's a dumbass brute force approach on packing spheres on a circle. But you see, although it starts to do something along these lines, it's not very pretty, and it gets slow like hell because it does not find more spots to put spheres on, and it's just not very optimized. So this was a situation I was in, and the only way I found out of this situation, a door out, was to start learning computer science. But today, unfortunately, now that I discovered Houdini, I can do something like this, and this is exactly what I always wanted to do, because it packs nicely on this torus, and I have control of all the shape and size and color, and it even animates on. So I'm very happy that I now have an environment where I can do stuff like this without reinventing computer science from the ground up.
So yeah, I think the point of this is when you're not having the right tools, it escalates quickly, as exemplified by this bit. This is actually when we two met in 2014 at a conference in Berlin called C4D APT2. Catchy name, huh? But really, this was one of the most brilliant conferences I've been to, and thanks a lot, Pingo. I'm not sure if he's here. Thanks, Pingo, for organizing this. And when you look at the audience there, yours truly with a bad haircut. And on the other side of the stage was this guy. And watch what happens in his talk. He starts off gently, like, I'm a designer as you, I want to do real interesting stuff. But watch what happens, and I cut to it when we were like 10, 15 minutes into the talk.
Because I can remember when I started programming in Cinema 4D with version 5, it was very hard for me to grasp programming because I'm an artist, I studied graphic design. So basically, the XOR is only a part of a half adder, and you have another AND gate, and then you have one half adder, and so you need another set of full adders, so it gets more and more complicated. It's very essential that you understand that it works like this. It's not magic. Okay.
So what is needed for us to deliver the work that we'd love to do without having to take care of memory addresses in assembler? A fusion of tech and art that we actually found in Houdini. Take, for example, this project that Manu did.
That's another thing that always, every After Effects user wants to do this. in 3D because you have plexus. Who's using After Effects? Nobody. Okay.
You should use Fusion.
And you want to do this in 3D because the options are just greater, bigger, and you want to do it. Here's another example of exactly the same thing, featuring a nice vintage Entagma logo, by the way. The thing is, I'm an artist, and I want to do this effect, and I want to put my time into designing the effect and getting it right and making it nice. But I found myself really drifting away into the land of computer science, as you saw in this talk from 2014, where I'm discussing memory addresses and pointers and C++ structures. And I mean, I'm very interested in this sort of thing, but if you are approaching an effect like this, and you have to create the tools to do it first, you are just putting your time into the tools. This is my very first brute force approach, and you see it's quite a bit of programming already in Python. The problem is, this is programming, but it is slow. It won't get you anywhere because all the points are compared with all other points, and it just grows quadratic, so it's not nice. So to a rescue, there is a technique called divide and conquer, and it's from programming. If you have a big problem, you can just split it in parts and tackle each individual part as a problem. And in this case, the solution to this problem is called a KD tree. That means you have all these points and you want to connect them, so you have to find the nearest neighbors to the points. And what you do is just you have the space. Here it's in 2D, but you can do exactly the same in 3D. You split it in half and generate a node in your tree. And then you split it again in the other direction, and you have two more nodes. Now you have partitioned already the space into parts. And I can go on with this. And that means I can quickly find the nearest neighbor because I now can discard a lot of the original points because I know if I want to find the neighbor to D, it's probably not in the box close to C. So I thought, well, great, I have a slow program, make it faster, let's implement this. And now it looks like this, because you have to implement this KD tree search. And A, it's not a lot of fun. B, it involves higher level programmatic concepts like object-oriented programming and recursion and stuff. So I understood that it's not a good idea to hack your standard software. Instead, use something else that is made for stuff like that. And this is how it looks in Houdini. It's 4 lines of code, basically. So the beauty of Houdini is this. It's that side effects gave me the near points expression. And this near points expression is the 400 lines of code you saw earlier. And it's done by people who really have a clue about programming, so it's a lot faster and it's more stable than what I came up with. So my takeaway point here is Houdini is not a 3D program. It's not a 3D app meant for people doing 3D, but it's a 3D operating system or 3D development environment. So I compare it to Visual Studio, if you're into C++, which you probably are not. But maybe you know processing. It's Java-based, and it's used for doing procedural 2D animation or 3D animation. 3D as well, but it's pretty much the same. It's an IDE. It's a programming language. In this case, it's a written programming language, and it's a standard library providing you with all the granular tools that are necessary to build your stuff. And then you can very quickly, with a very little code, come up with very complex stuff. And in Houdini, it's probably pretty much the same, but in 3D, and you have different means of putting your code in. You can use nodes, you can use VOP nodes, you can use VEX, and this makes stuff easy while preserving all the power that you get if you program on your own. Here's another example. I wanted to do these VORONOI remeshing things, because I like the structure so much. And so again, I sat down again, wrote a plugin to do this effect. And in Houdini, I encountered, well, there is this checkbox.
Well, you implemented it in Houdini as well.
I actually first prototyped in Cinema 4D my tool, then brought it to Houdini, where you perfectly can do exactly the same with Python, all VEX, and I wrote all of it. And then a friend of mine gave me the hint, why don't you just tick this checkbox? And We'll just do it for you. The takeaway point here is Houdini does not only provide you with tools like Kai showed us, high-level tools like hair grooming or character tools or VORONOI fracturing, but you have all the low-level granular little bits and pieces of the large, vast field of computer science that you can use to build up your effect, the thing you have in mind. And that is one thing that is so excellent about Houdini. So if you're new to Houdini, what happens then?
Well, when you're new to Houdini, the questions you ask yourself is where do you find Houdini? And usually you find it in your task menu. It's very close to excellent software like Taptile, Thunder, Fox, or Chrome, or whatever. It's here. So you double-click it and almost immediately are confronted with this. And the standard expression or the standard impression that you get by this tool is this. You're like, what on God's earth? So, seriously though, how do you learn? Should I, just for the photos, please? So seriously though, how do you learn this stuff? And there are two competing schools. So there's the only true way of learning Houdini, because there can only be one true truth. And that is understand everything on a fundamental level. Well, I'm not a scholar of that school, so here is the only true way to learn Houdini, because there can only be one true truth. Ignorance. On a fundamental level. And ignorance doesn't feed into stupidity here. Ignorance is more along those lines of what Manu mentioned with divide and conquer. It's a concept that you do not only encounter in computer science, but also in physics, math, chemistry. So when you have a problem, you break it down into smaller parts. So breaking down, learning Houdini into smaller parts. The beauty of Houdini is, if you look at it as an operating system with individual tools attached to it, which the contexts are, you can just occupy yourself with learning one tool after the next tool. And these are the main contexts that you see here. And my recommendation is to start with SOPs first, that's surface operators. They hide mostly under the geo node, amongst other nodes. And they give you the possibility and the power to create geometry, be it volumes or be it meshes. And the beauty of starting with only this thing is that you have a limited subset, so you have to only occupy with that stuff. And also, you can always export geometry from Houdini, which gives you the power to use another tool for doing stuff that you haven't learned yet or that you find too scary yet. For example, you could export your geometry into another tool and shading, lighting, rendering it there. Or you could import geometry from anything like 3D code to Fusion to whatever. And SOPs teaches you two things. It teaches you the language that side effects uses in Houdini, and it teaches you this in a very accessible way, because you always see what you're doing, because you're working on geometry. On the other hand, it teaches you a certain way of thinking, a certain way of problem solving that the guys who wrote and developed Houdini think you should adapt to. So these are two things that you can take away from this. But the single most brilliant idea behind Houdini
is for me to explain.
Absolutely.
So Moritz is telling me it is SOPs first, but fuck. Even if you just focus on SOPs and you open this, I mean, it's only halfway through the menu.
Yeah, I wasn't telling the whole truth.
It's so overwhelming. It reminded me of the very first time of something like this, and I was just like, no, but no problem. Because it's not about the individual nodes, it's about the principle. And something like this is so much easier to understand. It's a piston cycle. That is the essence of an engine. That is what you have to understand to use it. And then if you manage to understand this, you can build up on your knowledge and you can look at one part at a time, and this makes sense. So the brilliant thing about SOPs is the interface. SOPs is just operators, but the big invention is the interface. They are operating on a standard data interface. So every node takes the same structure of data, can do something to it, and then gives the same structure of data away. And that means that SOPs in reality just boils down to this. You have an input, you have a very great operator if you use one of side effects operators, if you write it on your own, and then you have an output. And I can extend this chain and I can put stuff down there to make it complex, but it is always the same principle. This is an object in the real world. Well, the rendering is not that photorealistic, but it's continuous. That's my point here. What computers do to represent this is they sample the positions, because computers work in a discrete way. We cannot store the complexity and continuous data that is present in the real world, so we just take samples. And these samples store the position of the object. And now we connect these dots with each other, and this is the connectivity information. Now I know this dot has a relationship with the other dot. And this is how geometry is represented inside of Houdini and in every other 3D program. The beauty of Houdini, though, is that it does not stop here. You can put other data onto these points, onto these edges called primitives, or onto the faces. So, for example, I can put color information on here. And in the moment where I put color information here, I can use the connectivity structure to my advantage, because now I can interpolate the colors. Because what I have here is a geometry, right? But I'm using it as a three-dimensionally bent image, basically. And my pixels are my points, and the connectivity tells me which pixel comes next. But this structure is so open and so versatile that it does not stop here. If I start to put numbers on my edges, for example, I can use these numbers to model a soft body. Because I can just say these numbers are not the edge length or positions anymore, but it's the K, the constant for the springs in my soft body particle spring system, for example. This is still very geometric because it's a soft body model in geometry, but Houdini is completely open, so nothing tells me that I cannot use exactly the same data structure to model flights, for example, an airline. These are the airports that I want to serve, and I have the connections. These are my flights. And I can use a blur node on flight connections in Houdini, because flight connections is just a standard data interface. And this concept is what makes the sub-context in Houdini so powerful. It is there in other DCCs. It's just that in other DCCs, all this data is always tied to UVs, vertex colors, geometric stuff. So you can do big-breasted elf women with bows on beasts, but you cannot do something like this. And this is why Houdini is open. It gives you a data structure, so you don't have to invent KD trees or quad trees or I don't know, but it gives you the possibility to augment this data structure with whatever you have in mind.
You can do that as well. But yeah. You want to do it? I do it? Okay, this is one of the setups that we encounter pretty often in our daily works, and it's a basic setup. When you want to grow something, you want to have ice growing, you want to have stalactites or stalagmites. Which are the ones that go downwards?
Tights.
Tights, stalactites. You want to have stalactites
it sounds a little bit like tits.
Seriously. So basically, you want
That's how I remember it.
What you end up with, what you want to end up with, is something like this. So kind of organic growth, but organic growth that's artistically tweakable. So you can just influence how the stuff grows, which structure emerges while it's growing, and which still forms the shape that you input into the solver. So ever needed organic growth? This is just the common setup in production. And here's how we did it.
A big yes. The problem is just how do I approach something like this, keeping in mind that I have a very versatile data structure, points and attributes in Houdini. The first thing is I have to be discrete. I have to have samples. So I fill my shape that I want to grow with points. And then I plant an infected seed, a virus in the middle, with one point having an attribute telling it to be a virus. And now I search for every point if a virus is nearby. And for some points, this turns out to be false, because this virus is nearby, but it's not inside of the site circle of the particle here. For other particles, it turns out to be true. Here we see I have an infected particle in the search radius. So the infected particle will put a little bit of its infection on the searching particle. That's why it got this pink color here. But it's only slightly pink because I have two neighbors, one of them being infected, one of them being healthy. So I form the mean value and put it on the new particle. And if I do this again in the next frame, now I reach a value where this particle reaches a certain threshold that I set. And once it reaches this threshold, it switches group. I indicate this by the orange outline. Now I have a second particle in the infection group. And now if I go to the first particle, which did not find infected neighbor, now it has an infected neighbor, and off it goes. Now the infection propagates through all my points. And as I can scatter points volumetrically in Houdini, I can do this in the volume. And that is basically the principle that is underlying this effect that you see here. So let's build it. I usually start in 3D code because I have no modeling department like MPC or the mill. So I am my own modeling department, modeling in 3D code, and then exporting the stuff to Houdini. The fun thing is that 3D code is already volumetric. In Houdini, stuff is usually too big, so I scale it down, and I have the model from 3D code here in Houdini to work on. Now I want to scatter points inside of this model. The problem is, later on, I want to cut my growth surface with this model, because I want these outlining boundary surfaces. So I will first peak this, and make it a little bit bigger before I scatter points into it, to have more growth volume, to be able to later on cut out the original shape, because I want only the growth surfaces to be new and everything on the surface should be the old stuff. Then I turn it into a volume, just gorgeous. In Houdini, I just put down one node and boom, I have a volume. And then the most natural thing would be to scatter points in there. So I have the scatter node, I append it, and I scatter points. They look regular, but in reality, if I turn off the relax iterations, they are just very erratic, random points. And in this particular case, this is not what I'm after, because crystals are very regular. They have a very regular orthogonal or tetrahedral structure to them. So I need something else. And in Houdini, there is fortunately a second node scattering points into volumes called the point from volume node. It's used for fluid simulations. And if I go down with the point separation, you see it generates a very, very even structure of points. That is exactly what I need, because I want the stuff to grow in orthogonal angles instead of just randomly throughout the volume. So now I have the seed points. I have to group them, because I want to go over all the seed points and look up the infection. I want every seed point to look if it's infected, so I put these in a group. Then I can later on tell the code to just run over these points and not over the infected points. And I have to set some attributes on them, because I want to somehow separate between, I want to know the infection status of every point, and I want some artistic control. So that's why I'm introducing another attribute. That's the versatility of Houdini. I can put on whatever I need, how much I need. And the second attribute is the speed, the growth speed. So you see here, I'm always using wrangles for this. It's so much easier than using other means of setting attributes. The infection is 0 as an initial value, and the growth speed is 0 as an initial value. But then I use a VOP to vary this growth speed. So this is the artistic control. Now I can map which parts of the volume will grow very fast and which parts will grow slowly. And this leads to these crystallized crystal structures emerging while growing. So the solver itself would grow spherically, but by using a Worley noise here, I can make it grow in cellular structures. The Worley noise is basically scattering points in the Cartesian 3 space and then looking up the distance to these points. And you see, it's giving me 4 distances. The method is currently 2 points. That means it's only 2 distances. And the very first distance that comes out of this node is just the distance to the point, which is circular. The second distance that comes out of Worley noise is the distance to the second nearest sample it finds, which looks like this. And if I subtract both of them, I get nice cellular structures. This works in shading too. It's the standard approach on these cell noises and stuff. And then I pipe it through a ramp and a fit just to be able to manipulate the value range. I want to actually tell Houdini how fast the stuff should grow, and I have this ramp here, the interface on the growth speed node that I can use now to map the values and just dial in exactly how fast the stuff should grow. And this can be a lot more complex too. You can put another noise in there, or even textures, or scan data, I don't know. It's up to you. Now we have the seed points prepared with my growth speed value, so the food points. Now I need the seed points. And I want to generate seed points only where this growth value is high, because I don't want to generate infected seeds that end up in areas where the growth is very slow and it takes forever for the stuff to start. So I use one of the new group expression nodes that are a godsend and just put down growth speed is higher than 3, and I get a group where all the points are grouped where the growth speed is higher than 3. And then here you see if I blast the stuff away, I end up with the areas with a cellular structure, basically. And now I want to select some random points from the cellular structure to serve as my infection points. So I use a sort sub, which just sorts the IDs of these points. And then I use another group expression and tell Houdini to just select the very first points in my array. So give me the very first 5 points that are in my long list of points. And so I end up with these 5 points. That's a nice way of getting random points from a bunch of points with a sort sub. I quickly put a sphere on the points now, just for you to see. These are my seeds. They are hard to see otherwise because they are so tiny. So the next step is to put, again, initial attributes on these seed points, because in this case, I want the infection to be 1. On the food point, we had 0. In this case, we need 1 for the propagation to work. And then I merge everything together. Now I have a big bunch of points. Some of them are food points, the majority, and some of them are infection points. Time for the solver. But before I dive into the solver and explain to you how this works, let me explain the other 2 nodes. I have this color by group here, which just states that the stuff that is coming out of the solver should get its color by the group. So if the group is infected, make it red. If the group is not infected, make it white, to be able to separate between the 2 parts. And then I have the blast that blasts away everything that is white, so that I end up with just the infected points after the solver. The SOP solver is actually not SOPs, it stops, but it stops with a SOP paradigm. So if you are learning SOPs, no, really, it's just easy, because inside of the SOP solver, you're using exactly the same ideas as in SOPs. So if you want to do simulation, and if you are sticking to SOPs, then by any means use a SOP solver wherever possible, because SOPs is a huge system. It's meant for collapsing bridges and millions of rigid bodies interacting with finite element solvers. Here you have just the basic idea that you get data from the previous frame. That is this purple node over there. So I have this white node that gives me the initial data, and then I have the purple node, and the purple node gives me the data from the previous frame. And that is what I need, because I want to accumulate these infection values. I want to look up the infection values and accumulate them on the points to be able to do this propagation growth. And that's why I have this switch node here. The switch node is just switching between the input and the output. And this is all the solver code I wrote. And of course, it's a little bit of writing stuff. It's more complicated than it has to be, because it's a lot of stuff that I just do to make it a little bit more interesting visually. In principle, I have this near point expression that I outlined earlier, which is just looking up the neighbors. And then I sample with this line, infection is point infect, I sample the infect attribute. I just say, hey neighbors, how infected are you? And then I have a little loop that runs, oh, no, that's not good. Now it will start from the beginning. But stuff like this happens. Any chance to move through this video?
I actually have no clue.
Yeah.
Give us a second here, while you entertain him.
No, that's not possible like this.
Why not?
Because, yeah, if you are not in this blöden Hint-Modus, dann kannst du spulen.
Okay. How am I supposed to do that?
I don't know.
Seriously?
I have just no clue. So the rest has to be imagination.
No, seriously. Does any one of you know PowerPoint? Wait a second. I can trim it here. Let's just hack it. Let's just hack it.
Like Houdini.
Super. Where have you been?
A little bit more.
Like there?
More.
Yeah. Out of the solver.
Yeah, stop.
Like there?
Okay, great.
Let's try this again.
So glad that I have a second language to fall back to if I'm excited.
Yeah, sorry for that.
So after all this solver magic happens, I have a second wrangle that just decides if the value exceeds the threshold, then please switch group. Leave the food group, go to the infection group. And now, more and more points are entering the infection group in every frame because the value is accumulated, it exceeds the threshold, and it goes to the other group. And I end up with this growth. And I can completely design it. I can tell the structure of the growth speed attribute. I can say where the seeds should start. I can map the speed it should grow with. But it's just points. It's not very pretty. So we have to mesh it. And it's exactly the same problem as with fluid meshing, because flip fluids are just grids of points too. So I use the VDB from particles node, which puts a sphere on every particle, and then represents all these spheres together as one side distance field volume. By the way, the resolution of the volume has to be smaller than the radius of the spheres to be able to represent the spheres, because if one voxel is the same size as a sphere, it's not possible to see this. And this looks nice already, but a little bit blocky, so I make use of an old fluid meshing trick that basically everybody is using. I make the volume bigger, so I reshape the volume with a dilate node, make it bigger, and then I smooth it in this bigger state, because smoothing goes with a little bit of loss of volume all the time, so that's why I dilate it first, and then I shrink it down. So now I have a smooth surface that is pretty much in the same location as it used to be, but it's smooth instead of blobby. It's really the look that you're after. And what I can do now is I have the original model, and it's all about keeping as much from the original model as possible, because this comes from modeling. There are weeks of work is in this original model, so I don't want to use this as my final result. It's just blobby. So I generate another SDF from the original model, so I have two volumes represented, two volume representations, and then just combine the two with, say, a Boolean operation. In this case, it's not a Boolean operation, which gives me this. Now I have the original model wherever the growth reached the surface, and I have the growth surfaces on the inside. And now I could map them with displacement mapping or whatever. I convert it to polygons, and in principle, we are done. Now it grows, nice shader, put a nice shader on, and that is it. The thing is, it's not as sharp as the original model. It's still not preserving all the details because of the step to converting everything into volumes and then converting back. So the last thing I do usually when in production, so this is a little thing that I would not put into an Entagma tutorial because it's just this extra production step, is to reproject the result. So what if I just take this result and then decide whatever is near the surface of the original model gets projected with a ray trace operation to the original model. And this is what I do here. I just sample the volume value inside of the crystal and decide the points of my surface. How deep inside of the crystal are they? I show it to you by just turning on color here. Wait a second, I jump out. And you see, now I have an attribute on the surface that tells me blue is very close to the original crystal, and orange is all the stuff that is newly created. And what I do now is I use inside of the VOP, I use the intersect VOP, that is basically the same as a ray SOP in SOPs, to do a ray tracing operation and just project the blue points onto the original model. And that gives me the fine, intricate detail back. And my model is not very detailed because I quickly threw it together. But if you have a very detailed model with little bumps and tiny stuff, this is really vital to do to have all this detail. And you can pick up other attributes like UVs too by this operation, for example. So here I show you the difference. With this switch node, I can switch between the two states with and without reprojection. You see, it's quite a difference. In this case, of course, it's not that tremendous, but imagine having really surface detail there. It's quite a difference. So that is the beauty of doing something like this in Houdini. Building the setup takes a half an hour, of course, after reasoning about the theory a little bit. But this is something that is just out of reach, or used to be out of reach for me before. And I'm just glad that I can throw together something like this with minimal coding in a very short amount of time.
Yeah, talking about stuff that we had never thought we'd be actually doing is this, because when you think about it, what you're doing here is taking a volume and then converting this volume into points, working on points and then converting it back to a volume. So why not try working in a volume altogether? So here's the theory behind it. imagine volumes just like giant Rubik's cubes. And each of those tiny cubes is just a voxel. So it's basically like a 2D image, only in 3D, like Photoshop for 3D in a way. And we're looking here at
Don't call Houdini Photoshop.
like an image processing thing for 3D. And we're just looking at a 2D plane here just for simplicity. So the basic algorithm is really the same. You just have your two attributes, which are two volumes here. One just stores the infection state, which is one infected voxel here. The other one stores the growth factor, so how fast should the infection spread on a given voxel. So the first thing you do is, for each voxel, and let's say this is our currently active voxel, we look around its direct neighborhood if anything is infected, and we find this. And after we found this, we look up at this place, what's the growth factor? And then we weigh it by the distance. That's the same thing. If it's farther away, it should contribute less, and add it to our current voxel value. So we're just adding stuff that's in the direct vicinity of a given voxel. So how do you weigh this thing? And calculating distances in volumes is not that straightforward, as in points. So there is this concept called a Manhattan distance. And if you think about a city map of Manhattan, you have this rectangular grid of blocks, and you cannot just go straight from one block to the next. You have to go through walls there. So what you do is take right-angled turns. And this is the Manhattan distance. So you're just counting the number of steps it takes you to get from one voxel to the next. So this would be a distance of 1, it's just one step. And this would be a distance of 2, 1, 2. And if you think about it in 3 dimensions, in the direct neighborhood of a voxel, the maximum distance you can have is 3, because you add to this, this, and this, one step to the next, or to the last plane of the volume that's directly behind or in front of it. The thing about working in volumes, though, is this: execution times. Volumes are huge. Volumes are just not this 2D image plane. They are just really just a cube, and they are just like image after image after image, if you think about it. And Houdini gladly gives you VEX. And VEX kind of is, in most cases, automatically multi-threaded. In the volume case, it multi-threads your thing. That means when you're running it onto a hefty machine with like 32 cores, you have 32 threads working simultaneously on the volume, which already gives you a speed up. However, as we'd like to work in intricate structures and have this tiny detail, you need quite high resolution volumes. So you're still a bit laggy, and lagginess is not what you want when you're trying to dial something in artistically, because you want to have instant feedback and you want to be able to quickly iterate. So let's look at execution times a bit, and in comes OpenCL. And here's the thing about OpenCL. This is new in Houdini 16. And suddenly when you dive into OpenCL, you see why developing render engines that run on the GPU, for example, takes time. The thing here is having fun in OpenCL without losing it. And this is the hard part. It is just figuring out the stuff, what you're supposed to do, how to get in data, how to get out data. The thing is, you have to just put on data on your graphics card, then you execute it on your graphics card, which has like 1,000 cores in contrast to 32 of your main processor, and you have to get the data back. And you run into problems because some of the stuff for some volumes, for some voxels, it's already solved, and the solver runs again on it, and it screws up, and it's just a mess. So there is this one guy on Vimeo going by the alias of Animatrix. I think he's a TD somewhere in Canada. And he put out this brilliant video where he goes over a smooth sub implemented in OpenCL. So thank you to you. Thanks for all this, Jonas. It's been a huge help in understanding this. So let's look at what I did here. You see this part is the volume part of the setup. This is the thing that Manuel has been talking about. And up here I just convert into volumes, and here I have my two solver chains. This is OpenCL, this is VEX. And in the solver, you see I just dropped down this OpenCL node, and in here goes your code. And it's quite a bit compared to VEX, and that is mainly due to all of the management stuff. You have to get data in, data out. You have to take care of solvers not interacting, not interfering. And I set it to 4 iterations. That is the same thing as running the solver 4 times each step. And the clever thing is data doesn't need to be swapped, so it's not bogging it down here. On the VEX side, where I dove into the solver, I did the same thing, just by running the solver 4 times. And as you can see here, the VEX code is a bit more compact. That's due to the fact that you don't have to manage all the data and all the concurrent programming stuff. So let's execute both in parallel. I'm going to go into a split screen, and you see on top, this is VEX, this is OpenCL, and let's hit play at the same time. And this is a medium res volume, I'd call it. And it's executed on a single GTX 780 versus an i7 6 or 8 core, I think. And you see the structure evolving, pretty much the same thing that we have here. Up here, it's at the second solver step. You have your first 30 frames rendered here. You see I did a bit performance highlighting there. And after this thing gets bigger and bigger, the convert VDB sub is what's breaking it down. So if you would cache that solver into a file, it would even run faster. So already approaching frame 50 here, and we're on the second frame up here with VEX. So this is the thing when working in OpenCL. It can be difficult to implement. For some things that you can massively parallelize, it's absolutely worth doing it, because you have like here a 40 to 50 times speed increase. So if you're into programming, have a look at OpenCL. It's really powerful. Try not to get too mad at it. So this brings us to our conclusion. What should you make out of all this? And we have 4 conclusions for you. The one being obvious is divide and conquer. This is something you can apply not only to Houdini, not only to software, but to your life in general. Try to break down problems and solve them one by one. The next thing is understand concepts over certain setups, because concepts give you the power to recombine stuff, to thoroughly understand stuff. And once you understood a concept, you're not bound to any software. You can implement and try to take it everywhere. This is geared to Houdini. It's an IDE. It's a development environment for 3D. It gets you mad when you think about it being your standard 3D DCC app. It is an environment that lets you play. It's like an operating system for 3D. And it's hugely liberating when you're just lifting all the bounds. Of course, it's a bit confusing. You have to make your way around it. But it's hugely gratifying and hugely liberating. So thank you for sticking with us. I'd like to thank Side Effects for inviting us. I'd like to thank, if there's any regulars on Entagma here, I'd like to thank you. It's amazing what we get back from the community. We're really thrilled. It's great. It's awesome that all you've shown up here. It's amazing. So thank you. If you got any questions, I think there's a mic. Feel free. Thank you.
And thank you for me.
We do have a few minutes for questions, guys. Any questions?
Whoops. No, nothing. Whoops.
One over there. Catch?
Yeah, sure.
It might be better for the audio. Yeah. For the video recording.
Danke.
Actually, 2 questions.
Yes.
Thanks for the talk. The first one is, how much is memory a problem with OpenCL when you're handling big volumes?
Of course, at a certain point, it's a problem.
Okay.
It's as much as you can fit on your GPU. It is, I found, decently efficient. I think I ran this on a 6 GB card, and there was room left for increasing this. What you can do is if it crashes, you can still run it on your CPU. I haven't run tests on how it compares to VEX, but the setups that I did for Entagma, which might not be what you're aiming for in production, they were easily executable on a graphics card in single one.
That connects to my second question. How much do you use Houdini in actual production?
Increasingly. That's the thing about Houdini. It depends on which state in the production you are. When we're doing concept, when we're doing creative work, when we're doing pitching, most of the time we are not using it, because we have some clients that require us within a day or 2 days to come up with like 30 style frames, and really different style frames. So you just want to slam them together. It's not like intricate production here and just this particle needs to go there. It's just like make the broad thing, render it out, and ship it to the client and see what he says. When you're in production, however, the image changes a bit, because when the client comes in and says like, well, I don't like this, how this particle behaves. This particle looks a bit too, I don't know. Clients. And you're like, in any other software, you're like, fuck, how? And in Houdini, it's just, find the particle ID, delete it. So it depends on which state you are in.
The biggest problem with using Houdini in production in a shop like ours, which is an advertising commercial shop, is tradition. People are not used to use Houdini, so it's hard to find freelancers for me, and it's hard to convert my employees to the idea of using Houdini because it's associated still with visual effects, very complicated, steep learning curve, stuff like that. And of course, other programs are faster in certain aspects of the pipeline, but it would be very welcome to use more Houdini throughout the pipeline. It's just that it's a slow process. People have to, learn to love it. And that's why we're here, to make you love it.
Yeah, but still, we had this one situation where we were really struggling to finish a piece in another tool, and deadline was just creeping and we had 6 weeks to produce this thing, and after 5 weeks, we're like, shit, this is 1 week until deadline. So we actually sat down 2 of our senior artists and just forced them to use Houdini with us.
Yeah.
And we had to produce the thing in 1 week, and on Monday we said, here, you're doing Houdini with us. On Tuesday, they were up and running. On Friday, we had the thing delivered. So once you give the people a chance to learn the software with you in a room, just shout questions. I mean, at least if you have the prerequisite, it's good to be fluent in another 3D app, so you grasp the concept, the general concept that underlies it. Yeah. But they had no problems getting up and running there.
I have another question. How much science behind nature of code, natural growth process, algorithms and formulas are needed to create interesting growth processes, and how much knowledge do you have about that, and what is needed for that?
It's up to you. It is up to you and to the papers you can get your hands on. I think this is already quite okay for motion graphic stuff or something like this. And then I think normally it's just a mixture of reading, what have other people found, and then your own ideas, and just mixing everything together, because this is just the foundation of growth. I don't know if you have seen space colonization, for example, which is the idea that you just remove the food entirely if it turned into infection with a radius and then connect the dots, and then you get these intricate coral-like structures. That's just an extension to this idea, basically. And you can go on and on and on, and diffusion limited aggregation is again something that goes along these lines. So what if you have a lot of particles that are attracted by the particles that are just growing, and then I can put them on, and they are maybe a little bit smaller, and they are not meshed in, but they are little poppy seeds that are on top, or the possibilities really are limitless without more knowledge or without making the stuff more complicated. It's just, let's try out this and that and this and that, and it gets more complicated.
I think to answer this in a more general way, I think what's needed are 2 things. On the one hand, the interest in the stuff, so the willingness to research that stuff, and on the other hand, the willingness to try and read through some papers which to me sometimes seem to be written in an arcane language to make it actually more complicated for people to understand than it actually is.
But again, divide and conquer. Just look at the pictures.
Yeah, divide and conquer. I told you, and you were mad at me when I told you, just look at the pictures of the paper and it's going to be fine. But seriously, that's my approach. I just go through the pictures first and see if I can figure it out, and then, okay, formula.
No, really, it is like this. I once implemented a paper for the parallel transport algorithm, and it's all fancy integrals and formulas and Jesus Christ. And I was like, fuck, I don't get anything about it. And then I just went on, and then they put just 4 lines of pseudocode in there, and I copied it, and it ran, and great, thank you for the paper.
That's the point. Most of these intricate mathematical problems are just like a nightmare to write down, because mathematics is about being precise and being about just evaluating it anywhere in space, which computers are not about. It's just discrete, it's just this point and this point, and in between interpolate. So when you're seeing code or something like that in a paper, this is your goldmine.
Yeah, pictures, code, and abstract at the beginning.
Yeah, exactly.
And whenever a strange Greek symbol pops up,
ignore it.
Cool, thanks for the tip.
That's only for the international recognition, I think. I have the feeling.
I'm not sure.
Okay.
Any other questions? One more? No.
That's cool.
Thank you, guys.
Thanks for having us.
Fantastic presentation.